Before we dive into a discussion on troubleshooting IPv6 end-to-end connectivity, let's review the different types of unicast IPv6 addresses that we'll find. So first of all, let's start off with the global address. And the global address is the addressing that we are going to use on public networks like the internet. These are going to be assigned by IANA, the same group that assigned the IPv4 addresses. And if you want to have an IPv4 addressing comparison, this would be like having your IPv4 public IP addresses. So the addresses we're using on the internet. The difference, though, is that with IPv4, we only use the public IP addresses on the internet. We use different types of addresses inside of our local area networks. However, when it comes to end-to-end IPv6 connectivity, everybody who needs connectivity to a public network will utilize global IPv6 addresses. So the end stations will be utilizing global IPv6 addresses. That's the plan. That's the goal. Now, we do have private IP addressing for IPv6, just like we have with IPv4. But it's not called private IP addressing. We call it unique local addressing. So these are going to be addresses that are routable inside our local area network. They will not be routable out on the internet. So as a result of that, we can have overlapping unique local addresses throughout the world, and that's not going to cause an issue. But let's think about it this way. If I am using unique local addressing inside my organization, what's going to have to happen in order to get on the internet? I need a global address. So does that mean that we're going to have to perform network address translation from an IPv6 unique local address to an IPv6 global address? Yeah, that's what would have to happen in that particular case. And we're trying to avoid that. So those devices that need internet connectivity should use a global IPv6 address. And then whatever devices in the organization, for example, your routers themselves, the router interfaces, they don't need access to the internet themselves. So as a result of that, then maybe we'll use local addressing for those devices internal to our organization that don't need connectivity to the public internet, like routers, management IP addresses, and so on and so forth. And then those devices that do need connectivity to the internet, we'll give them their global addresses. So kind of a different approach than IPv4, where IPv4, everything inside our organization had private IP addresses, and then we did network address translation. But we don't want to use network address translation for IPv6. So essentially, anybody who needs connectivity to the internet gets a global address, and then those devices that don't, we could use unique local addressing on those particular devices. Now, we also have the concept of a link local address. Essentially, this is an address that every single device will assign itself. So every single IPv6 enabled interface gets a link local address. So if our router has 4 different interfaces, it's going to get 4 link local addresses. Your PC, if it has 1 interface, it's going to get 1 link local address. If it has 2, it's going to get 2 link local addresses. So what are these link local addresses for? Well, they're automatically configured by the device for the respective interfaces that are enabled for IPv6. And the scope of this particular address is for the physical link only. What this means is that we can communicate with devices in the same local area network using these link local addresses. So we don't need global addresses. We don't need unique local addresses if we plan on only communicating inside of the local area network. But most of us are going to be communicating outside of our local area network. So we're going to need more than just a link local address. But everybody assigns themselves a link local address for various services and features that can run within inside of a local area network. So for example, our routers. Are we going to use a global address or a unique local address as our default gateway? No, we don't need to. We can just rely on the link local address because any device inside the local area network off that router interface, well, they're going to be able to reach that router's link local address because that interface is part of the same local area network. So you're going to see on a lot of devices that the default gateway is one of these FE80 through FEB0 addresses. Why? Because that's all you need. You don't need a unique local address or a global address. So anytime you're using features or services or trying to communicate inside your local area network, you don't necessarily need that global or unique local address. You can get away with the link local address. You'll see later on, as you look into the dynamic routing protocols for IPv6, like EIGRP for IPv6 and OSPF v3, what you'll find is that the next top address is the link local address instead of a global address or a unique local address. And the reason why is because those two routers are connected to the exact same link. They're in the exact same local area network. So as a result, if I'm trying to send a packet to the next hop router, well, it doesn't need a unique local address or a global address to talk to it. I just need its link local address. And that's what is utilized with those dynamic routing protocols. So you'll see link local addresses used extensively when there is services, features, protocols running within the local area network, and you only need that link local communication. We also have reserved addresses, and there's various reserved addresses. You have reserved addresses specifically for Anycast communication, for multicast communication. So that's beyond our Unicast address types. But essentially what you need to realize is that there's tons and tons and tons of IPv6 addresses. And some of them are simply reserved for various features and services and functions like multicast. We can use some for Anycast and so on and so forth. But typically what happens is with Anycast, you can use any global IPv6 address for Anycast. You can use a unique local address for Anycast. Essentially, you just have the same service, the same server providing or similar servers providing a similar service, or the same service, pardon me, and they're using the same address, so that way there you'll always access the nearest resource to you. For example, like with content delivery services, if we have a streaming media service and we have it in North America, well, we might have a data center set up in New York. We might have one set up on the West Coast of the United States. Let's say it's in San Francisco, and then East Coast users contact New York, West Coast users contact San Francisco. But essentially, they're using the same addresses, Anycast addresses, so that way there what will happen is as we're communicating, we go to that nearest device. So it's just an example of how we can do that. Now, loopback, instead of using the entire 127.0.0.0/8 range, it's just one single address, :1. So if you want to test the TCP IPv6 stack on your local device, you can pick your loopback address for that. And then the unspecified address of : is really similar to the IPv4 address of 0000, meaning I don't know my address. So if you see an IPv6 address that's 0:0:0:0:0:0:0, so 8 zeros, essentially that's truncated down to : So you'll see : that just simply means I don't have an address right now, so I'm just communicating with all zeros. So it's an unknown address. For example, with IPv4, if I'm sending a DHCP discover message, I don't know my IPv6 address, so it's sourced from 0000. Likewise here, if I'm sending out a packet but I don't have an address yet because I'm trying to get information, well then I just put : in the source field of that particular packet. So these are some of the different types of unicast addresses we're going to be dealing with, especially global and link local on a regular basis. And if you choose to implement unique local, then you'll definitely have to become familiar with that as well.